Hello everyone, my name is Hossein Zargar and I'm excited to share our research with you. It's deep learning in early stage structural performance prediction. Let's start with an introduction. Here you can see a couple of buildings. We want to design them in parametric way using computational tools. All these buildings have performance feedbacks that are needed in early stage parametric design. So as engineers and architects, we need this information. The older way to get feedbacks is running multiple simulations. It's accurate and solid, but not efficient time-wise, especially in parametric workflow that multiple parameters can be changed during design. So how about learning from simulations that already exist? First, we are going to learn from stored data, and then let's predict performance. We are going to do that in a step-by-step process. We learned from other machine learning methods and we borrowed some information from them. All of these deep learning projects have one thing in common: using existing data to train and then to predict new objective. The objective can be categorizing different objects, like in self-driving cars, or in our specific case study, predicting the embodied carbon. So in overall, we need data. We almost have parameters for training well-known deep learning architectures like language processing and face detection. Of course, there are still under development too, but in building design, the story is different. We need to know what data type and what morphological information is needed for achieving a good prediction. In every parametric design workflow like Grasshopper, what data type is accessible in earliest stage of design, of course without a lot of effort. How accurate the prediction will be, and how different parameters can increase the accuracy. How we are going to do this? First, we started with generating a parametric design space. 946 different building geometries are generated using 7 main variables. We are focusing on timber buildings, a construction material that is still under development for real-size building design. As an improvement over previous research, our current methodology can handle more irregular shape of building geometries. Then we calculated the amount of embodied carbon, and in the second step, we extracted new variables. This step is necessary for doing a machine learning prediction task. We had main variables from previous step, and we categorized the new ones based on mass and frame inputs. Here you can see part of mass variables like slicing 3D geometries in 3 different axes. And as shown in blue color, we have some frame inputs related to a structural form. Then we took 20 different combinations of these variables and trained neural networks to predict embodied carbon. Here is a combination of mass and frame variables, index 9, and this one is index 14, another combination including 9 different inputs. We used these combinations, we trained the networks, and by comparing the estimated embodied carbon with calculated one, we can investigate the effect of different input combination on prediction process. So we talked about inputs. We have 20 different combinations of them. How about neural network architecture? We used 5 different optimization methods, including ADAM and RMS probe, and combining with different hidden layers configurations, we generated 500 different outputs. The output is estimated embodied carbon, and it's ready for further investigation. We grafted all models based on mean absolute error in training and testing. These are all 500 models. Ideally, we want to reduce error in testing phase along with acceptable performance in training. So we want to find a dot that is lowest as possible. Our best possible tested model looks like this. Here you can see hyperparameters used to train this model. We had one hidden layer, and RMS probe with momentum was our optimizer. In the left, you can see the predicted versus actual chart. A 100% successful prediction task will generate just one line, but here you can see 10% error range. As you see, best tested model is not best trained one. Here is best trained model. And this one did not do quite well in testing phase. It's due to overfitting that could be investigated in all deep learning projects. But what we really want to do here is not just finding best models for prediction. As mentioned before, we want to find out what type of variables will help us to have better models for prediction. So as you see here, If we are going to use just main variables, the result for best and worst tested model will be like this. Here just mass variables, and finally the frame ones. So let's have a deeper look. Here you can see all models trained and tested based on main variables. And then by using only mass inputs, we will see improvement in testing phase, and that's valuable. And finally, our models based on frame variables. The result is quite interesting, especially comparing mass and frame variables. It's easier to extract mass variables compared to frame inputs like a structural shape of a building. I'm talking about number of beams and columns, characteristics of a structural core, and all computational costs needed to have extra frame-based inputs. So if we could enhance the accuracy of model just by adding easily extracted morphological variables like mass-related ones, then it will be valuable in early stage design phase. And here is our final results to put it into context. There are 3 different building categories. As mentioned, the algorithm can handle irregular shapes and it's focusing on timber buildings. What we see here is we can get fairly accurate predictions using any of these variable types. It's due to systematic analysis of hyperparameters and variable types to achieve best prediction models. And that is interesting, especially focusing on how accurate we can have prediction using just mass variables. Massing variables are easy to extract. There are initial characteristics of every 3D model in early stage of design. So there is no need to build very complicated simulation models. In this methodology, we can use data from previous models for predicting the performance of new designs. And that's what we want to do in future. That was my presentation, and thank you very much.